So I brought a material with me tonight from a recent project. It's made of compressed activated soil. It's heavy and dense and about twice the strength of ordinary concrete, but I think of it as being soft. And I'd like to talk with you tonight about why that is and how softness holds the key to addressing the major challenge facing architecture. Many of you probably passed a building site on your way here tonight. It's a common sight in a city that's rebuilding itself constantly. And it represents a big opportunity to replace older, poorly performing buildings with more efficient, newer buildings. These new buildings often require much less energy to heat, to light, and even to cool, if that's required. But as we focus on the operating impacts of buildings, so the carbon that we emit as a result of heating and lighting, we have to also take into account the embodied impacts of the materials that we use to build the buildings themselves. And this is especially true as the operating emissions go down. All we're left with are the embodied impacts of the materials, and these can be really significant. So this is both the raw materials as well as the energy required to produce the glass, steel, and concrete in the picture behind me. And if we look at all of those materials around the world, we get a really startling picture. 40% of all resources on the planet go into our built fabric. So rethinking materials is the key challenge facing architecture. So if we look at concrete, one of the most common construction materials on the planet, we can see just how this plays out. So we use concrete for a range of applications, from building structure to sidewalks. And to produce the concrete, we have to mine limestone that has stored carbon safely underground for hundreds of millions of years. We apply heat to that limestone to produce cement, and that entire process generates about 7% of global carbon dioxide in the atmosphere. That's a huge number from a simple material. So let's look in contrast at how the human body makes bones, the structure of the body. The body absorbs through biomineralization the nutrients it needs for the bones from the tissues immediately surrounding. The bones are dynamic and grow with the body, and they're strongest where the stresses are highest and most porous where the strength isn't required. So they're calibrated to the function in very fine ways. And at the end of life, the bone biodegrades, adding nutrients to its local environment. So a process that creates no emissions and biodegradable at the end of life. So what if we produced architectural materials in a similar kind of way, using feedback loops between the building and its immediate environment, the building site? I call materials that engage matter in feedback loops with their environment soft. They require advanced sensing to accommodate the rich complexity of environment. And the interrelationship of matter and information operates in conjunction with biophysical systems, instead of seeking to overpower or obliterate them. So let's return to the previous example of concrete. One of the ways that we use concrete really widely around the world is with concrete blocks. And we can look at the kind of way we manufacture those because it's instructive. First, we start by mining limestone in the example we saw previously. We convert that to cement through the application of a lot of energy. We truck the cement to a block production plant where we mix it with washed sand and gravel, which we wash to remove any kind of impurities from the sand and gravel. Once we produce the blocks, we ship those via trucks to the building site and we build the building. At every stage in this process, we're applying large amounts of energy to eliminate the natural variation. And this is a kind of good example of the old, hard, centralized approach to manufacturing architectural materials. It's sort of like McDonald's, everywhere the same. So what if we rethink this process? Well, we might start by saying, could we use a range of soils instead of one type of soil, of washed sand and gravel? Could we apply dynamic data processing to characterize the behavior of natural clays in the soil instead of applying resources to wash them out of the equation? Could we activate those same clays instead of using Portland cement? And then when we go to make the blocks, instead of making blocks that are virtually the same strength around the world, could we make variable strengths based on the function that we're asking the blocks to perform? So we might have structural blocks that are stronger and ones for partition walls that are weaker. Finally, could we use distributed manufacturing at the building site? Since we're using the site soils to make the blocks, could we distribute that manufacturing to the building site itself? Well, a few years ago, I co-founded Watershed Materials to rethink the manufacture of construction blocks along a soft paradigm. And so we're using soils at the site, we're applying nanotechnology and geochemistry to activate the natural clays and completely eliminate the need for cement, which accounts for about 90% of the impacts in a typical concrete block. We know that we can do this because we've been doing it for about 10,000 years. So rammed earth that uses naturally occurring clays in soils as the binding constituent is one of our oldest building technologies. And what you see on the wall behind me is a project that I built as a graduate student at MIT that doesn't use any Portland cement at all for binding. It relies entirely on natural clays. So this is a third-generation block press prototype as we sought to commercialize this kind of technology with the support from the National Science Foundation. And we're using these computational protocols to adapt to a wide range of site soils to produce blocks with the same variable strengths that we were hearing about a moment ago. So we built a few demonstration homes. This one is in Napa, California, and this one's in Sonoma, California. And what you notice in this picture is that when we eliminate the gray Portland cement that provides the binding in most conventional blocks, and suddenly we begin to express the natural geological attributes of these site soils, so the building itself can actually connect to the regional specificity in a geological sense to express the unique site characteristics. So we've looked at a soft alternative to a structural material. Let's look at another material that's central to contemporary architecture, polystyrene foam insulation. We're using massive amounts of this to actually, ironically, to reduce the ecological impact of buildings from an energy perspective, because a well-insulated building requires less energy to heat and retains that heat longer. But manufacturing polystyrene foams requires carcinogens and neurotoxins that are toxic to humans and animals alike. It lasts for hundreds of years, despite an average age of commercial buildings in Canada that's currently 40 years. So it starts out like this, but it soon winds up like this. So what if we could apply the soft paradigm to the production of polystyrene insulation? It turns out that you can grow insulation with a fraction of the impacts from a blend of mushroom spores and sawdust. So my team of researchers at UBC are looking into this now, and we've shown that it can be done. The process takes no toxic chemicals, no additional energy inputs. It's endosomatic, so it's drawing from the metabolism of the mushrooms as opposed to outside or outward application of energy sources. It takes about 5 days, and at the end of that, we have a product that looks a lot like polystyrene insulation. We can mold these mushroom materials into virtually any shape. So we produce some furniture as a way to kind of show how to maybe recontextualize the material. And we put this in front of the bookstore at UBC for about 3 months last summer. But what's really exciting to me is the potential these dynamic materials have if we can make them go dormant through, say, genetic modification, so that during the life of the building they're static and performing their function, but the day the building is demolished or we no longer have use for it, they can begin to actually actively digest the building, which is the role that the mushroom plays in the forest. We've seen how a soft approach can limit the impacts of some of the most notorious materials in architecture and construction, from concrete to polystyrene foam, and the impact they can have on energy, impacts to environment, and biodegradability. Collectively, this set of behaviors might change our conversation from one of limiting the harm the built fabric produces on the environment to engaging in a positive relationship with local ecosystems. And if we jump scales and zoom out, what we might find is that the built fabric itself contains one of the greatest promises of addressing global climate change. So carbon-positive buildings that store in their very fabric more carbon than they release to the atmosphere could act as the carbon sink that we desperately need to address global climate change. Thank you.